turn blue, and that's good. Because you know, I have a blue suit on. That's good. I try to match my mic signals, you know, indicators. If it was red, it would be a problem. I don't get a lot of red. But I do have red here. We bring up the red as usual. But so first of all, the notes get all the way around. Did everybody get notes? Okay, just extras. Pass it forward. I'm going to put it up here. Probably. You want more light? No, we'll try. I'm trying to remember the lights over. I think there's this whole panel stuff here. What? Can you do that, or do I need to do it? Like, window shade. That's much better. Yeah! All right. The only problem with opening the shades is you're reminded you're asleep. You know, it's like, I have 3 huge windows in my office, but it doesn't mean I get a lot of light. Okay. So, were there extra notes?
I put them up on the projector.
Where?
Where you got it?
Oh, you put it up here?
Yeah.
That was confusing. Put it up right by where I go, right by me. It's like my wife says she puts up notes and she's asked about something. So why do you take care of something? I mean, you don't know about this. I put a big note on the refrigerator. Well, why would I read what's on the refrigerator? It's like it's got lots of stuff there. Why should I do something for me? So I just, you know, I'm working on it. So if you're gonna put it next to me, how am I gonna find it? Okay. So you're traveling incognito. Okay. So, okay. How's everybody doing? It's Monday. But it's stats! Right? Really, stats would be like 9 a.m. Monday. Start the week. Like, you know, give that charge you need, you know, to get you going for the week. Okay. So interim report 3, how are you feeling about it? I didn't get all my emails today. Was there one from you? I was supposed to see it, but I've been in meetings. I didn't get a chance to go to the emails. Okay, so I apologize for coming back to you, but just know you're not alone. I somehow forgot to get back to Robbie, and I did see his email, and I had time for him, and I was getting back to other people I forgot, so I apologize. Whoever just came in, you did. But it's okay. Stay good. Questions from having done or having desperately been trying to finish the report 3. What are your questions?
So, I guess, just to be sure, I was running like some tests and regressions to like start finding variables. And on all of my adjusting variables, I got the p value of like 0.0000.
Okay.
Is that bad?
Okay, so first of all,
I was just practicing.
I know, practicing is dangerous. Okay, so I will explain why. It is very hard to remove debris from your brain. This is one of my theories in life. Once things get into your brain, it's hard to get it all out. It's a lot like Windows, right? You close programs and you think it's all gone, but little bits of different programs tend to stay around in memory. If you don't do a whole boot, you know, sometimes you have to do a boot because everything's still filling up and messing up your memory, right? So and then you have to reboot to get rid of it. So if you run regression, so if you're running like it's supposed to be like your final analysis, and you're not done yet, the problem is what happens if you then find a variable or something else is going to change? You can rerun it, but once you run it, your brain's already working on, oh, this must be because of this, and this is because of this. And I can guarantee you, no matter what the results come out, you will come up with great reasons why it should be that way. Okay? You'll run it and say, it's not significant at all. Oh, of course it shouldn't be significant. That's because of A, B, C, and D. And it's amazing how well you can come up with those ideas. And then you find out there was an error, and you run it, it's all significant. Well, of course it's significant. Those things weren't real problems because of, you know, E, F, G, and H. Right? So you where are these reasons? But once you have those reasons, those experiences, it kind of lingers in your brain. And it starts start to shape the way you're thinking about the results in the problem. So then if it was wrong, and my concern is that then when you run it for real, you may still have some thoughts from an incorrect analysis still linking friends. And that's why I usually recommend to do your best to hold off running the regressions till the end, even though it's incredibly hard not to. Like, it's like, how am I ready to go? I want to find out the answer already. Okay. P-values all being 0 is not necessarily problematic. There's lots of things that you run, and when you start looking at age, race, sex, education, and income, there's a lot of things where, it's incredibly related, like education and income, will be related with having greater source of health care, having health insurance, and use of professional health services. I mean, there's a lot of things where, it's associated and expected, and expected to be different. So that's fine. So seeing p-values, those 0 says, well, done, of course that's related, and of course, you didn't have any follows. It wasn't study variable, you have an adjuster, exactly. Because it's associated, that's why you want to make sure you have any follow. So that's only alarming if some of those variables you look at and you say, well, I thought it might be associated with that. No. The whole point of the adjusted variable, right, is because you think it may be associated with the outcome. That's why it's in the model at all. So that's the role of the adjuster. The role of the adjusters are to say there's other effects that have an impact on the outcome. And because it could be not evenly distributed across my study variables, I'm concerned they'll end up being a bias. One will get too much or too little of people with that characteristic, and it will bias the results. And so we had it to the model. So the fact that it's significant really means that it increases the importance of the adjustment. If it wasn't significant at all, it would say, it turned out it didn't have any relationship with your outcome. You wouldn't end up with any real bias if you didn't account for it. Because it turns out it doesn't have the impact on the outcome. Even if it was differentially distributed between study groups, it wouldn't matter because it doesn't have any effect on the outcomes, so who cares? When it's significant, that's when you say, darn good idea to put that in the model. So that's good. Okay. Questions, comments? Okay. So that's case. There is in your souls mentions this homocyclic particle. Okay. What I'm going to do is give you like a 60-page report and that's about 8 tables, do summary. So what I'm going to do is I'm going to, I really wasn't happy with the article, I didn't have chosen last week, it's better later today. So then I'm going to post, I'll post a couple of articles. This is not required. What we're going to ask is that we get an opportunity to people to, so that we'll try a couple articles, have a couple people, have a couple groups of students who want to try to work together. This is just short. It's only a handful of slides, so I'm just focusing on it. This is based on who they study. These were like 1 or 2 hypotheses. That's it. Only zooming in on one key main part of the outcome, and then presenting the results on the paper and discussing those things. Interpreting the outcomes. It's really, really short. You have to just share it together, and if you do it, whoever does it will get an extra 2 points. Right? It doesn't matter whether you're full score homework or low score homework, you'll just get 2 points. But it gives you a chance to actually article, get a little practice. So I'll get that loaded up later today. I'll send an email out and then respond to something. The downside is this year when it works out, which I didn't have to change it, but this is Thanksgiving week, which is not, which is Thanksgiving week. That's what that is. Why? It's not a requirement. Okay. Just guidance for your project presentation. For your project presentations, right? As it's on the syllabus and as we discussed time, right? It's Monday, December 16th. Scheduled 1 to 5. It should not be done to 5 o'clock. They said that at the beginning because I don't know who classes. So my guess is we'll probably be done for 30, but in any case, but it's blocked off 1 to 5. And you're going to be split into 2 rounds. Here, and I've also reserved the Biostat Department conference room, which is directly across the hall from the MPHP office, on 5273, and also here. So Zoe will be in that group, and I'll be over here, for your project presentations. Now your presentations have a very set structure. Please note that it is not going to be presenting all your project. Get used to that when you have a presentation at a conference, or you have a capstone presentation, you're going on, you will not be able to present all the work that you did. You'll have to be someone else. So, certain block of time, that's it. Your project, 7 slides. They should be timed to 7 minutes. Okay? And then break down slide background, slide for motivation target audience. While motivation and target audience blends into the background with a written document, the oral presentation is quite fine. You have to go through so one slide for that. One slide will have one aim and the hypotheses associated with one regression. So you're only going to end up discussing the results from one regression. Now, if you have multiple hypotheses like the education, so forth, but it's all related to one regression model, then that's fine. You list multiple hypotheses. Remember, it's only going to come from one regression. Most of you will be writing 2 or 3 different regressions in your project. You present one. You get to pick which one. Okay, I'm waiting for you. So, slide describe example, 1 slide for regression results, slide for presentations, and a slide for normally, if you were doing a presentation, right, you're going to be virtually, right? We wouldn't just discuss the presentation, we also talk about the strengths and other aspects. But this is a trimmed down version that allows us to get into one afternoon. Okay. So we'll put these 7 minutes, and then there's time for some questions. And usually what happens is that students don't ask any questions to anybody. We'll do a couple of talks that will talk some questions. Usually happens is that I'll ask something, just comment on something. It's located, okay? I don't have like the spotlight, focus in your eyes, and then say, "What do you mean it's a logistic regression?" So relax. It's very pleasant. Okay, especially after you do it. Then it gets much more pleasant. But this is really, it's always like, that's your chance to shine. gone through, done a lot of hard work, and you finally get to the point where you're actually getting some real answers to your questions. And that's like the fun part. So, reporting linear regression results. The title of the table should indicate how compared. Saying linear regression results is not a very good table for the results. Right? Rather be looking at I think that's the end. Right? But I don't think it's pretty descriptive. I'd rather see something where the title indicates what your out here was. It's a model of what. If you're looking at, impact of obesity, or you want to look at outcome. You're trying to look at diabetes, which is the obesity related diabetes, and you want to look at the title of convention diabetes. So say, over here, model for diabetes. For the study variables only provide the results. Results are provided with the coefficient and even. That's standard with any linear regression. There's always a coefficient of even. Sometimes, not infrequently, but not always, people will report confidence interval for that coefficient. That's fine. It's not required. Very common. If the model is for prediction purposes, then you really have to report model R squared. Give an idea about how well the model is explaining the outcome. If it's not for prediction purposes, it's optional. I like the word. In the text note table, you would state adjusted for and list your adjustments. That's the only place the adjustments show up in your results table. One line at the bottom. Then you want to answer by the title, you will put down, or by the column, or coefficients, or someplace it says model adjusted for. Okay? In the text, you comment about the results. Linearity, we'll talk about today. If linearity is, there's a concern about the problem, then you report on the test for it. But we're going to go through that today. There's no reason to believe that's going to be a big problem here. Those are the basic guidelines for linear. Table 1, then right, have that. Hopefully, your report 3 has a fully good table 1. And that describes your sample. It includes all the variables that will show up in your analysis. So that means your outcome variables, your study variables, and your adjustment variables. Usually, you'll start off with your more basic description, your socio-demographic variables and first. So it's which includes a lot of your adjusters. Also, and then your evidences, but often adjustments, but it's other adjustments. So to start off with your socio-demographics, then you'll get to other independent variables, study variables, adjusters. You kind of end up leading up to study variables, and finally your outcome variables. So that variable will be the last. Study variables before that. First, start with just doing socio-demographics, and adjusters, so basically describing your sample. Occasionally, people have other variables in there that may not be used in your analysis, but help make some point about your sample that people may have some questions. But for example, comment on it if it's not technically an analysis. Most of the time, only variables that are actually included. If the study is a comparison of 2 or more groups, right, and for each variable table 1, compare use 5 variable median. Okay, And that's what that was a constant solution. Down library analysis. It talks about choose, right? Okay, we just here. Often what's happening, especially in complexity logic study, so a lot of times on paper, there's one thing that you try. It's a study really about the gender. It's a study about gender differences in some and there's something right. Very often that is a autonomous categorical variable. When it is, then that becomes subgroup using one. So in addition to overall results, we have results broken down by these subgroups. So if you're like we had a chapter student, a big thing is going about gender differences and delaying care, showing up for care to check out symptoms of possible colon cancer. So there was a lot of really focus around the gender differences. So since that's a focus of the study, those become subgroup problems. So the overall results, reporting your descriptives for all those variables for the whole sample, you also want to report those descriptives stratified by gender categories. When you do that, you'll then run, additionally, bi-variable analysis. Now, please note the name. Bi, right, to variable. Right? A bi-variable analysis really means that you're doing analysis between two different variables. So the bi-variable analysis arose, in that last case, which was gender, then she had a whole bunch of other items like experiencing different specific symptoms. So then there would be all these tests to check was there an association with those symptoms or other variables associated with graphic? Are they associated with gender? Since you're focusing on gender, one of the things to look at is in this sample, how do the genders compare? How are they different in these samples, in those subgroups? T-tests, chi-square tests, ANOVA, all the stuff we did before regression, really, linear correlations, these were all examples of bi-variable analysis. So that's what you use to do those bi-variable analysis. Use whichever method is appropriate. And then you either make a column for the p-value, like I suggested, but it's also common, especially when you have a lot of columns, for people to just indicate which ones are significant by using asterisks. And the tradition is that I think actually, some people also use the 3 asterisks if it's less than 0.001. But sometimes you just use an asterisk to show which ones were statistically significant. If you've got a study which is a trial, clinical trial, and you'll see, it's like, here are the different groups. Intervention, control, right, multiple arms, more than 2 arms. And they'll look for to see, are the groups different? And they'll be doing all these bi-variable analyses, and usually they'll just indicate with the asterisk, whether there are significant differences. So, those are okay. Use the p-values. I recommend it here just by using p-values. The asterisks are also common. So the question there is there a variable that drives it? Now, if it's a continuous variable that's really driving it, and you're just saying, then, right, you don't have these different subgroups, right? You just have this continuous variable. So then, what you would be doing is looking at those variables. What are the meanings of that variable? Each of those groups identified by the variables. So if you're going to look at race ethnicity from the variables you did at one, your study was looking at systolic blood pressure as a continuous variable, and you could look at what was the mean systolic blood pressure in each of the race ethnicity categories. And then you could do an ANOVA to see whether there's something different. So instead of having frequencies broken up into multiple subgroups, categorical variables, just what's the mean for each of those levels. Okay. Another example, but I emailed you another example of groups. And this one, so we have age, which is categorical, and then dentures, yes, no. There was overall, and then I broke out by gender. So we had the overall. So what this is doing, the ends of the percents, right? So this column represents all the descriptives for the whole sample. This column represents the descriptives just within the males, and this just within the females. Now, most of your variables, they're not continuous, they're just going to be running crosstabs. Yeah, age is a continuous variable, but that will be different. Then you run a t-test with the difference in males and females. Otherwise, you do crosstabs. But if you do a t-test or analysis of variance and continuous variable, when you run it, included in the output is it's going to give you the means in each of the subgroups. So it will provide the numbers you need to pop into your table. Same thing here, when you run your crosstabs, if you run it this way with group one as the columns, right? Your column percent, or your table, you get to pick all those percentages across the rows and columns. The column percent is going to be the numbers you need to fill in the table. So it's important to we have this because your study is focused on males and females. People will want an idea how do males and females differ.
How do you handle this table when you have people who each one of these has maybe BC values? So different outputs broken down. If age had three BC values and then age had seven.
Right. If there's a small number of missing values, it's not a problem. Okay. So this is one reason why when you see ends and percents, sometimes in variables, you find the same ends in different variables. You can find that percents don't match up exactly because of that exact difference. Because the missing values, there was the denominator. So it's not a problem. If you have a variable that has a lot of missing values, particularly, so then you may want to designate the variable, n equals. Okay. Linear regression results from sample, right? Is that you have to do the coefficient p-value, and it's common, but a rule that you provide the confidence interval as well. Okay. I can give model, give the intercept, give the study variables. And model was adjusted for age x zero. Right? Results for age x zero are not provided. Okay. Interpret that. So, you tell me if the linear regression model for physical attractiveness, okay, says a continuous scale may outcome variables physical attractiveness, years of calculus study, so could you interpret that coefficient? You can pass. You can try or pass? Okay. So, Katie. Okay. This is a chance to say yes, and then I go on, right? Okay, you tell me if you interpret that 6.2. Well, first of all, what kind of regression is this? It's a linear regression, right? So the outcome is what kind of variable? That's right. So it's a scale, right? So linear regression means the output variable is continuous. So now let's try it again. 6.2. Oh, Sloan, you want to try now? Go ahead.
I believe it's the for that when I'm not
forget this. Swap. Right? It's for each additional year of calculus, the score of the physical attractiveness scale goes up by 6.2. I mean, isn't that everyone's experience? So, okay? Right, so the coefficient, remember, if you think about the regression equation, the equation is the intercept plus this times this times this. So this is getting multiplied by this variable. So 6.2 times each number here is added to your score for your output. Okay. Reporting logistic regression results. Again, title, good idea to have it include, indicate what the output variable is, you'll know what the model is for. There are some exceptions in terms of, like sometimes you're going to be looking at multiple outcomes with the same variables. They have a couple of regression results, and so they include in the same case. But even then, there's usually a theme for what your output variables are, so there's still usually some kind of title that's a little more meaningful than just saying regression results. With the study variables, right, usually with logistic regression, you don't get the intercept recorded. So, yeah, just study variables. Give the odds ratio and the confidence interval. That's the standard for logistic regressions. And sometimes you give p-value, sometimes you don't, you just give the confidence interval. And then again, in the note below the table, say what the adjusters are. Again, comment about the results in the text. If it's for prediction, you'll give a report something known as a C-statistic, which you didn't do yet, right? Logistic regression model for success in life. Okay, this is based on years of data, years of population-based data. Let's see. I'll take it back to this. Okay, actually. So tell me first, you just interpret for me, does it look like the model is doing a good job of explaining the outcome? Yes, because. Well, the p-values will tell you whether variables are significant. You can have variables be significant and still not explain them all. So what's the model, the overall, how well the model is? Adam, what you said? Because I think it's again, okay, Shannon, it's your chance. Rise and shine. Oh, okay. Right. Right. Okay. Where is the indicator? Oh, that's right. You didn't do the C-statistic yet. Right. Sorry. I had to switch the orders of things because we had cut short last week for the capstone presentations. So there was another 30 minutes of lecture that was cut out. It was supposed to be in there. The C-statistic, right? Okay, fine. So let's go to the interpretation. So Adam, taking stats with Mendel, how is that associated with success in life? Well, this is going to be a yes/no variable, I think. Took stats with Mendel, yes/no. 6.2 times the good compared to people who take that right. These are conventional stat people. Realize how privileged you are? Okay, so people who took stats with me have 6.2 times the odds of having success in life. Yeah. On the other hand, okay, Gina, your turn now. Okay. eating potato chips for breakfast. Is that, first of all, is that associated with success in life? Right. So is it, like p-value small, it is related. And can you interpret the odds ratio pretty quick?
There's
Okay, now, saying something is 0.25 times the odds isn't necessarily the clearest way you would get. So instead, you have different ways to handle it. You could say it's 1/4 the odds. That would be one way. Usually what I do is when for odds ratios and relative risk, anything up to 2, I prefer the method of the percent higher or percent lower. So in this case, it would be 75% lower odds, right? Starting from 1 down to 0.25, it's 75, 1 minus 0.25, it's a 75% reduction in odds. 75% lower odds. Less, right? So that works good. The odds ratio is 1.4, 40% higher odds. It's a little bit easier. You're still not talking about odds. It's a little how easy it is going to be. Good. Interaction terms. Interaction terms, right? We have done for the effect of some variables could be different for different groups. For example, impact of social support on health may differ for men and women. So if you feel that strong social support that has more of an impact on health in women than it does for men, then you say that there was an interaction term. Social support may have an overall effect on health, but that impact may be bigger or smaller depending on whether you're about men or women. And in the case mental health study found was there was a difference between the fraternities and sororities and the beneficial effect on groups like this. Yeah. What? Well, if we put in the effect of gender, we put in the effect of social support, we have the overall effect of each. But we're not accounting for what happens that it may be different when people have higher low values of social support for men may be different than the ones for women. They're just looking at them independently. It's saying the effect of social support, if you don't do the interaction curve, you're saying it's the same regardless of gender. Whatever benefit social support does is equal to the men and women. The interaction effect is a way to say, no, you know what, it's actually, it behaves, its benefits are different. It's a modifier. Yeah.
Sorry to interrupt. Can we go to the previous slide? What was the language you used to interpret the first odds ratio taking class with you?
Right. So people took stats with Mendel at 6.2 times the odds of success in life.
Okay.
Compared to people who
Okay. Just the language.
Good. Okay, the way you do an interaction term is you just multiply the variables. So you just do a transform compute in SPSS. You just say, okay, here's my new variable, and it equals variable A times variable B. Social support times gender. That's it. That's all you do. Create that new variable, and then add it to your model. So that new variable created as a multiplication is added to your model. So here we have one before we dealt with. Impact of smoking, of course, on FEV1. We think maybe the impact of smoking is different in boys and girls in the study. How do we incorporate the interaction effect? So we create a new variable, we just multiply. Sex variable times smoker, yes, no variable, multiply it. and then we'll add it to the model. So I'm going to show you, you can follow along. But transform compute, and that's what I mean. You type in the name for a new variable at the top left, and then the expression you just put in. Sex times scope. That's all there is in interaction terms. It's very simple to do, but again, be very judicious about the use of interaction terms. There should really be a strong basis for hypothesizing interaction effects. They turn out to be much less common than people might think. And you have a bunch of variables, right? I mean, there's a whole slew of interaction terms you could look at. And then just the model gets really crazy. So here, sex times smoke interaction term. So the first crosstab was showing you there were 21 males who smoked. And then when they did the multiplication, because male was the 1, female was 0, you see when we code, we get 21 down. So again, every time, whenever you do any kind of recoding, creating a new variable, you always want to run the descriptives to check to make sure that your new variable has been computed correctly. So if this was the original model, smoker was a variable, and we had sex in there, you know, we want to do an adjuster. Now we're saying is what? We're actually interested in that interaction term, that probably a study variable, that there with smoker times sex. If this is the case what you're looking at, there's a good chance you might really consider sex to be a study variable. But whenever you're doing something interactions with variables, it's always have each variable in there separately by itself. Oh, that just is the main effect. It's just the variable by itself, as well as the interaction term. So the interaction term is added. It doesn't replace the individual effects. Okay. There's interpretations there already. So now, this actually illustrates something nice that, so you do it, when you want to look at the top, the interaction term, not significant, not even close, right? And lots of interaction terms. Look at the significance of smoke. P is 0.067 in that model. When you don't include the interaction term, it's not here. When you make an interaction term, and they're not significant, a lot of times it happens, but some of the effect of the main effects gets sucked into that interaction term. And so now what's happening, so then it takes away some of the significance of the main effects. Another reason why you want to make sure when you have an interaction term that there's really a solid basis for considering.
So how did you get to the p-values different? How did you make smoke an interaction term and not something model? You created a variable for
That's what I showed before, the transform compute and just create a new variable and multiply.
And
it.
so if you run, is this on a different test? Like if you run a different test, will it know that smoke is now an interaction?
Well, the interaction term, as far as SPS is concerned, it's just a variable. The fact that I computed it as a multiplication doesn't matter to the calculation. Once you've done that new variable, it's just another variable, just as if you had observed it and recorded it as one of the original variables. And it gets treated exactly the same way, just another variable. Is that okay? Not convinced from your facial expression.
I guess, does it become like a new variable? If you're kind of
Literally.
doing?
Transform compute, you make a new variable equal, multiply the two variables, and now that is it. That's a new variable. And it exists in your data set. It's in your data set along with the other decoding variables and so forth.
And then you just run any other test
You
with
just
that.
use it, treat it from then on forward, just like any other variable. Yeah, maybe.
So if you do an interaction term, regardless of just like a linear regression, your study variables would be two interaction, the interaction term would be two separate data.
Right, they'd all still be included. Right. We never drop the main effects just because we're looking at interaction. It's additional. Yeah. Well, if they're all study variables, you would be, you wouldn't need to be looking at all of them. Right? The only study variable would be included. Show the time. That thing. Okay. Yeah. Is that okay? Yeah. Okay. Great. Multiple regression. So if we're doing multiple regression, right? So that's what we've been doing now. We have multiple independent variables, study variables, adjusted variables, and that's great. One of the complications is referred to as a linearity of multilinearity. What I'm saying here is sometimes you have a model and two, or more of those combinations. It could be linked to two variables that are so very, very strongly correlated with each other. I'm talking about only amongst the independent variables. Okay, so amongst the independent variables, you can have two study variables, or a study variable and an adjusted variable. You can have two variables that are very highly correlated with each other. And if they're really, really correlated with each other, right, the effects can be kind of confounded. That it gets to be, they're so associated with it so strongly that it's hard to know is the effect in one variable or another. But if they're strongly correlated, that means when it comes time to look at the analysis, it's also hard to say, well, who's responsible for this effect? And what happens is the coefficients can sometimes come out. The model will predict fine. Prediction will not be effective. But it's having trouble knowing which of the effects is due to this variable and which is due to this other variable. So it could apportion it incorrect. So it could be one, let's say there's no effect, combined effect. It could come back with one being a really strong positive effect and the other being a strong negative effect, and they balance each other out, and there's no effect overall. The net effect will be correct. That's not a problem. The method you use for regression won't be effective in that respect. But when you go to interpret the coefficients, you've got one big positive and one big negative, when it may be that they should both be basically zero, no effect. That's the problem when you have this collinearity of associations, and suddenly the coefficients individually, the interpretation becomes problematic. If those are both adjuster variables, it doesn't matter. The only problem you can have is the interpretation of coefficients. The model will predict fine. It will adjust fine. The adjusted variable is aren't the issue. Also, the only issue could be won't be interpreted. Will coefficients be effective? Well, we'll only interpret study variables. So the two variables that are associated are adjusters. Not a problem. Only when a study variable is involved. If a study variable is involved, now we're concerned that we will attribute the effects incorrectly in our interpretations of the study variable. That's a problem. And it may be that things are so confounded, you cannot distinguish between the two. And that can be problematic. Okay, so linearity, we said, doesn't affect prediction. Problem is interpreting the coefficients. And there are simple ways to check whether linearity is a problem. That it takes really strong correlations to be a problem. So that's the good side. Like if you were just doing pairwise correlation, correlation, it really becomes a problem. Usually it's not until maybe about 0.7 or something correlation. Really, really common. Okay? But sometimes you still get some effect even from like correlation over 0.5. So you do get gosh. So, hands up with her.
I was just wondering if you could give, like, I'm thinking, like, I don't know, I'm thinking of, like, race and income or race.
You know, race and income, those things don't usually follow. There's a correlation, but it's not so overwhelmingly strong. strong that it's present in the column. We're talking about more things like, usually they're like things that are measuring very similar constructs. And sometimes if you're looking at, not always, but I'm just wondering, maybe, you know, systolic and diastolic blood pressure, they don't always have to go the same. But really, really often, they do. Or let's say you have a single measure of blood pressure, or let's say you have blood pressure on 3 different days for each of the variables in the model. It might be a very high correlation because blood pressure, right? So do a pretty high correlation sometimes in like WHO data, right? I think between like adult literacy rate and adult fertility rate, things like they were really high, you know, correlation. And we also find so, but it has to be like really, really strong. Not just that. Well, we know there's a lot of association. It's got to be really high. There are certain measures which are just the kind of things that you talk about in everyday conversation, like the variance in place factor, eigenvalues. I mean, hardly a day passes that I don't have a good eigenvalue call from somebody. And then the condition index. Whatever. There are some different methods people have created and they provide scores. And SPS can generate those scores, and then you can take a look and see whether there's a problem or not. Sometimes the variance relation factor can be difficult to apply or down. We're going to take a look at it. So, let's see, we can do this with it's just all on screen. And linear regression on the statistics button. One of the options that people, you know, pass over how to do those, you know, we're always checking like model fit in R squared, and that was all of that, right? Linearity diagnostics, you have a box you just check off. When you check it off, part of the outcome will include running with those different tests. So when you do it this way, okay, so you get the table at the top, for the most part, looks like your usual one, but it added on 2 columns, tolerance and variance inflation factor. Okay? It's just reciprocal to each other. But the variance inflation factor is the one that I said use. We'll use rules of whether it's greater than 5 for your problem, others use 10. You know, if it's over 10, it's usually a problem. It's between 5 and 10. You can also just run the model with and without one of the variables that's where you have a problem to see how it affects it. But one thing to keep in mind, right? 2 variables are so strongly correlated, you don't get a lot of extra mileage out of having both variables in the model. If they're so highly correlated, the explanatory capability can be captured by either one. You don't really need the other one. The other one's not going to add much if the 2 are so strongly correlated. They're telling the same story. So it's really that high to be a problem. Usually don't use much of a problem. Which is the simple solution to the problem. Here are the eigenvalues. When we talk about being a problem being close to 0, this still isn't really, it's like a bunch of decimal places over. So the condition index 70, right? Before it said about 100 to 1,000 would be moderate linearity. So not quite up to the beginning of a very wide range of moderate linearity. So it's really not a problem. So this is expected to be at least about the decimal place over so these are just some rules that you can check. Again, if there is a problem, usually just drop one of the variables that's causing the problem. The C statistic, this is really important. The linear regression, so the R square was a very nice measure to use to see overall how the model do. The outcome. So So in logistic regression, you can have as the same kind of photos example. There are various metrics people can use. And I think of them, the C-space is probably the most appealing and the most so it is a measure of how well your model discriminates, right? It's a logistic regression, you're trying to have two possible outcomes. First, you're trying to discriminate classify into different buckets. How well can you classify? So it does this analysis where it takes, it looks at, instead of all possible pairs of cases in which the probability of the correct case is greater than or equal to the probability of an incorrect case. What that means is it takes observations and takes all cases where you've got the zeros and the ones and sort of pairing off goals, people, failures, and successes. And what we'd like to see is that the people who had the events tended to have higher predicted probabilities. As we compare it up, people who didn't experience the event and the people who do experience the event. And then for each of those observations, all those pairs of observations, what was the probability from the model according to those characteristics of the people in each of those cases? What did the model predict was the chance of the event? How often was it the people who didn't that end up with the case in real case? How often did they have higher probability of having the getting the case? So all the observations, once you've done your model, you can assign from the model predicted probability for each observation. If your model's doing well, then the people with the highest probability of getting the event should be the people who, the most people with the event. Right? You want to see a matchup of people who do experience the event should have higher risks than the people who didn't get the event. So that's what you're looking for, some congruence between what did happen, the people who got foods, of the people who got the event or not, and to the model predicting the risk of the event. Are the higher risk people tend to be the ones getting the event or not? If you have your model and it turns out that the people who have the lowest probabilities of the event were just as likely to get the event as everybody else, you've got a pretty lousy model. If the model is completely worthless, then you'll end up with 0.5. And it's all over. Okay? So the idea of a C statistic is going to be that it will then is that it ranges from 0.5 to 1. 1 would be great. And every single pair I came up with, every time, people who got the event, higher risk of the event than the person who didn't. So 0.5 means it's just chance. The model doesn't help at all. It's not accomplishing anything. 1 is doing perfect. So here are some interpretations. Now, keep in mind, right, I take some liberty here. These are not formal terms. Like, something's there is not what you can only find in a textbook. I've had people interpret words, quote that in ways that it seems like they feel like, no, that's what they call it. It's like, no, it's just my friendly way of saying it. Okay? Too good to be true. Now, when I say too good to be true, it's because it usually is too good to be true. That usually when you see things like this, it's pretty rare to get that high. Either it's something where there's good reason to expect it to be that great, but usually there's error somewhere. So, that's cool. But the main thing is that 0.6 is where you kind of start to say that, okay, there's some value in model. It's not going to be great, but at least there's some benefit. There's some explanation. 0.7, you start to think that that's a good model. 0.8 is excellent. So like the model with taking stats with Mendel taking for success in life, like C with 0.8, because it's such a good predictor, because it's a model. Right, that's a little rough way to interpret. Unfortunately, in SPSS, it's not part of the standard logistic regression output. I'm pretty sure I checked again with universities here, hoping maybe it would have it. It is not. It is actually still simple to do. It's just that it takes 2 steps. You have to run the regression a certain way, and then you have to pick another option. And I think we can do this time to go and step you through it. So it's a good time to break out your computers, break your computers, and open up the WHO kit. Things often get messy now. Parts all jack it on. Pull that blood blathering the SPSS. Take a break now? I mean, the sense I'm getting is that maybe it's a good time to take a break, even if timing-wise it's not quite not as far as things go. I usually like to get it to be at least halfway, maybe just a little bit more. But should we just take it now? Okay. Some definitely yeses before. So why don't we just take a short break and I'll see you in an hour. Tell me where you guys started. Okay. Welcome back. If you're sorry you returned. No. Okay, so open up SPSS. We will be using the WHO data. So get that all set up, and then I'll go through the key points to know about R first before I illustrate it. Thanksgiving? Yes. I guarantee you, when you're spending time with family over Thanksgiving, you're going to be talking eigenvalues, C statistics. It's like you have all this stuff to share with your family. It's just a little service I provide. Going? Mine's blinking.
I wonder if it's low battery. I have extras.
I'm not low battery. I can charge.
I just put that.
Yeah, battery, the protocol.
Okay.
With battery, I'm not sure if battery light comes on when it's good or bad. But right now, that light's off. I thought it was solid before. Have people notice?
It was solid.
See? That's amazing to me, right? Like, I would never. It's going.
Where do we get these lectures?
Okay, what?
Where do you even get these lectures? I don't even know.
These what?
Like the lectures, where do you even access them? You're recording them, right?
Oh, we're going to be getting things. It wasn't really for this class. The reason I was recording was there are two reasons. Occasionally something happens and somebody ends up having to take a different stats class, and they end up getting almost no regression. So this is going to fill in the gaps. The other thing is 405 next year is switching semesters. Next year, we're going to put health behavior is going to go to the fall semester. Looks like. It's not guaranteed, but it seems that way. The health behavior will become a fall semester course. You get it the first semester, and stats will go into the spring semester, is what's expected. And then the problem is going to be that there's going to be somebody who was trying to graduate in January and didn't take I was planning to take my class in the fall. And there's going to be a couple of people, so we'll record these lectures so they can watch it. So if you're watching these and getting the immense benefits from seeing this, just thank your lucky stars. You don't need to be an Amazon Prime member to stream this. Okay. So the C statistic. The way we're going to do it is in two parts. The first part will run a logistic regression, but we're going to tell it to save the predicted probabilities. That was the whole issue before, right? That we want to be able to take matching up the people who had the event, the people who didn't have the event, and check their probabilities according to the model. So when you run regressions, you can save different outputs. So we're going to have it save those predicted values. And then there's another option in SPSS for ROC curves. ROC curves is something that you do like in health views in diagnostic testing to see how well a particular test is working. So one way of doing it is, right, you want to compare to see of your test how many false positives you have and false negatives you have and so forth. Right? Well, that's really what we're doing with logistic regression also. So we can take advantage of the fact that the method for calculating this already exists in SPSS. We just need to take certain steps to be able to use it. So we're going to do this in two steps. We'll run logistic regression until it's to save predicted values. Then we'll run the option for ROC curve using the, and then with a certain settings. So let's just go ahead and do it, and you'll see how we do it. So I want you to go in the WHO data and go to regression binary logistic. And when you get to the screen, give me a nice smile and wave. Okay. That was nice. Too bad that wasn't caught on the camera. It's facing the wrong way. I think we need to have two cameras at multiple angles for every class. But okay. So when you get there, oh, darn. Did we get it eventually from the last time? Do you have East Africa there or not?
Yeah.
That you had. Region numeric was the problem. Maybe it was or something. Whatever. Okay, fine. Good. So you have East Africa. Put that as a dependent variable. And we have two of the variables I'm asking you to put in as covariates.
I don't have a per capita piece. I don't even know.
I think just use the, there's somewhere else. That's just in hundreds. Sorry. Per capita income, there's another one. Just not in hundreds. Right? There's another variable. Gross national income, yeah, okay? Just use the gross national income. It's the same thing. I just have it, I recoded it and changed the units. Okay? Because otherwise it gets funny with all these decimals because the units are large in dollars, so I changed it. But, okay, so you've used gross national income, that's fine. Okay, so do you have that? Okay. So now I have is, so click on save. Do you get something like this?
Yes.
Phew. Okay. Okay, my anxiety level just went down. Okay. So predicted values, check off probabilities. So that's all we're getting. We want every observation to have what its predicted value was based on the model that gets created.
So it also has the option of including the covariance matrix
Really? I didn't even see it in this one. This is from the previous version, but that's fine. Whatever. Makes it happy. So it has the covariance matrix? Okay. Where is that added?
It's the bottom checkbox
Okay. That's nice.
under export model.
Under export model. Oh. Okay. Fine. Don't bother. So we're just going to check off the predicted probabilities. That's the only one we need. Okay? Now, then when you go back to logistic regression, you have another button for options. Right? So when you're here, right, you have a button to the right of say you hit the options button. And when you hit the options button, now I'll tell you the truth. I think I've already confessed that I don't think much of the Hosmer-Lemeshow goodness of fit test. So, whatever. You know, it makes it happy to run. That's fine. Doesn't bother me too much to see it in the output. Anyway, I tend not to really pay much attention to it because I use the C statistic and idea about how good the model actually works. And finding whether or not the model overall has any value, and it just doesn't add much to it because I have a good measure of how well it works. And you have the individual significance test for each of the coefficients, you know, for all the coefficients, all the odds ratios, we can know whether it's significant or not. So I don't really need the Hosmer-Lemeshow test. But do check off, though, the confidence interval for EXP of B, right? The exponentiated coefficient, that's the odds ratio. So we want to check off, we definitely want confidence intervals for the odds ratio. I mentioned the linear regression, it's sort of optional whether you include confidence intervals for coefficients. In logistic regression, it's mandatory. So, okay, that's the whole key at this step. I'm not going to be doing a stepwise regression. You can ignore all that stuff at the bottom. And the include constant model, yeah, just leave that checked. And we're not trying to do a no intercept model. This is good. Okay. So that's it. And after you've done that, we can run it. So if you go ahead and then continue and run the logistic regression analysis. So first it comes, like we've done before, it's going to tell you, here's the original value, the way it's coded for your dichotomous variable. These are the values that are actually in your data set for your outcome variable. And this is the way it gets treated by logistic regression. This row is the one that will be considered the event. We'll be getting the odds of getting that outcome. Now, if your variable is 0, 1, and 1 is yes, and 0 is no, right, and 1 is the event, 0 is not, then you're fine. Right? This will always work out. But if your output variables have different values, then you have to watch it. It may be that, you know, there's a 4 and a 6. And maybe you wanted the event to be the 4, and it's going to come back with 4 and 6 and make the 4 a 0 and the 6 the 1. So it's good to just check it, make sure it's right. But if you have it as a 0, 1, then you're always going to be good. Hosmer-Lemeshow, yeah, whatever. If in this case, it's comparing the predicted to the actuals. I mean, it's not without value, but so it compares your predicted, what's predicted to what actually happened. The null hypothesis is going to be that your predicted model is just perfect. Everything is going to be good. And if it rejects it, actually, I'm sorry. It's checking for the differences between predicted and actual. So the null hypothesis is that there's no difference, which means that the model's good, right? And the alternative would be that the predicted and actual are really far apart from each other, in which case we're saying the model isn't good. So here, in this test, the significance comes out as 0.03, and the Hosmer-Lemeshow test would say, you know, this model isn't very good. But my experience is that it is not infrequent when Hosmer-Lemeshow says the model isn't good, and I get important information out of it. So like I said, I tend to just ignore it. Comes back, here's the regression outputs. Right. So this equation here is the regression that it ran. When it does logistic regression, right, it does this transformation and makes the outcome variable the natural log of the odds, and it does linear regression in that transform model, and you tend to say, you know, whatever, just run to the right part of the right half of the output, and because we want to see what the odds, we look at the odds ratios instead, and those p-values, the confidence interval, and we're okay. This is the, right, is just for the transform model, like, whatever. What's significant here? What variable in this model is statistically significant? Population in urban areas, that first row, right? The first row, the significance column, the p-value, right, is 0.038. So that's significant. Your gross national income, right? You get the same p-value? What? Yeah? Right, okay, like I said, it was just, all I did was change the units. So it was just, you know, so it's divided by 100, whatever. So, okay, so we see one variable has significance. Constant doesn't, the other variable doesn't. The odds ratio is 0.944, right? So for the percent urban. And for income, it's 0.993, but it's not significant. So let's interpret for the percent urban, this, we're getting this odds ratio. What does that mean in more meaningful English, as if we spoke English at all? I only say more meaningful, it's a relative term. Okay, because it's all odds ratios. It makes it hard. So Steph, are you feeling bold? Are you feeling like you have a pulse? Okay, pulse is all you need. So if this is the odds ratio, do you think you could interpret this? Good, you take a chance. Take a stab at it. So the outcome is East Africa. We're just looking at characteristics associated with being in East Africa. That's not really an outcome, right? So, okay, so the, right, so we're talking about, this is all going to be, right, we're talking about odds, we're talking about all the odds of that the country, given these characteristics, is in East Africa. So, okay, so go ahead. 0.6% less, right? So the odds are of being in East Africa are 5.6% less, right? The 1 minus 0.944, 5.6% less for each 1% increase in urbanness, right? And what for each additional percent of the population lives in urban areas. So this is per percent. When you have a variable which is continuous in a logistic regression, you have odds ratios, it can be misleading. Sometimes you get these odds ratios and they look like I've had like you do it for age and you get an odds ratio of 0.993 and it's significant. And you go, what? 0.993, it's so close to 1. And it's like, well, yeah, but it's per each year of age. So each year of age may be very tiny. But for 30-year difference in age, it's not so tiny anymore. So the way you could do it is, we talked about this before, was that instead of doing it for reporting it as as how much the odds are reduced for a 1% increase in urban population, you could do something like 10%. So if you're going to do it for 10%, we don't multiply by 10. It's raised to the 10th power. Because this is the odds each time you do it. It's 0.944 times the odds. Another percent increase, another 0.944 times again. So if you're doing it for a 10% increase in urban population, you take the 0.944, raise it to the 10th power, and that's how you describe it. So some people will do is they'll change the variable so that the units are changed. So like I did with the income and made it into hundreds of dollars rather than just dollars. They may change it and say, I want to look at 10% changes in urban population. How many tens of percents they are. So instead of, there you take all those percent urban, make a new variable where you divide by 10. So now 60% would be 6%. And the reason being, when you get the results, it will already be the result of the odds for a 10% increase. Now your 1 unit increase in that variable actually represents 10%. So you can change the variable and run it, or you can just raise it to the 10th power, and that works. Okay. And percent urban was, so we did that. And then it gives this classification table, which I don't really care about. You may care about. There's sometimes when it may be useful. And what that's doing is saying, if you say, you tell me what's the cut point you would use to take the predicted value based on the model and say, we would predict the event would happen. So the default is 0.5. They can say, well, if a person with these characteristics, the model predicts a greater than 50% chance of the event happening, then you would predict the event happens. And if it's less than 50%, we say it's more likely not to happen, so we predict it doesn't happen. And then it matches up the predictions against what happened. The problem I have with the table is that in most applications have the majority, if not all the people, have less than 50% chance of things happening. That a lot of times the events that you're dealing with are just not these super common events. It's only a minority of the population that ever experiences the event. So if you're looking at risks of heart attack or stroke, and it's still, most of the people, a majority aren't going to have it. So if that's what you're doing in your study, right, the probability, it's not really that you're looking at more than a 50% probability of having a heart attack in the 3 years that you're following up for the study, because you don't expect more than half the people to have that. So it just ends up being kind of useless. So I find most of the time, for me, it doesn't actually have any value. But there could be certain applications where that would have value. Okay. Well, when it ran it, it saved those predicted probabilities. So I have the information I need to be able to then go back to SPSS and run this. Now, I think graphs, it changed the screen, right? It says there's like 2 options, but one of them may be legacy dialogues. Is that correct? So click under legacy dialogues. Is there an ROC option then towards the bottom? And it's in there. Let me.
And there's bar, line, curve on.
I'm trying to remember where it was. I hate when they change those things. Analyze. Yeah, I was just gonna. That's what I was gonna check there. It should be. Oh, it's on the bottom of analyze. There it is. Okay. So they moved it from graphs. So now it's under analyze. So analyze, very last option I think it was ROC curve. So if you click on ROC curve, it's going to come back. Now remember, the whole point of the ROC, right, which comes from receiver operating characteristic, or receiver operating curve, whatever. So I think it's receiver operating characteristic was the original one. I think it had something to do originally with radio waves, but or something. But so the ROC curves, what happens is you're going to have what the prediction is and what the actual is. And diagnostic testing would mean, like, here's a test that we're looking at using, and then we have a gold standard somehow where we know the true case, whether the person has disease or doesn't. So there's the truth, or in our case, what was observed, they had the event or they didn't. And then we have the test for it, the screen for it, which is going to be our regression model. And then we're going to see how we do. So over here, right, so what we're going to do is put in for your test variable, and this should be at the end of your data set of variables, because when it created that new variable from the regression, with the saved predicted probabilities, it should be at the bottom of the list, right, the last variable. So that variable you put in as the test variable. That's our test. That's the thing we're using to predict. Then we also have to tell it how to figure out what the actual outcome was. So predicted probability, that's test variable. Your state variable, that's telling you what's the true state that that observation for each person. They had the event, they didn't. Or in this case, it was in East Africa or it wasn't. What's the true state? And that is determined by the variable East Africa. And then you have to tell it what is considered a positive result. And here, right, the positive result, right, is 1. That's the event. And most of the time, that's what you're going to have, okay, for what you're going to be running, especially when you follow my recommendations and you're always having your outcome variables coded 0, 1. So then the 1's going to be the event. 1 will be the value of the state variable. It's only when you have other codings for your outcome variable that would be different. So that's routinely for you, logistic regression. Test variable is the predicted probability. The state variable is your outcome variable from your logistic regression, right? And the value of the state variable will be 1. And I don't think we need any other options, so I think you can just run it at that point. And if you run it, hopefully you'll get this. And what we're going to want is the area under the curve. And the area under the curve is the C statistic. Okay. So here, the area under the curve is 0.786. Now, just pointing out that in this particular case, if you look at the classification table and you saw the percent classified correctly, it would be a number very similar to this. And it's a complete coincidence. It just happened to work out close. Ignore it. It doesn't mean it's supposed to come close, right? They're doing very different things. Just ignore it. C statistic is 0.786, so it's close to 0.8. And if you check back to Mendel's slang terms for C statistics, right? Like the 0.8 was excellent, right? So it was it's like, darn, that's good. Okay, you can quote me on that, right? No. So the logistic regression actually is a very good one. Now let's keep in mind, right, when we did the Hosmer-Lemeshow test, right, it was trying to tell us it wasn't very good, right? So, and here we find out is actually, no, it actually is pretty good. Granted, there was only one variable that added value to it, but it turns out that the one of the distinguishing characteristics of East Africa from other parts of Africa was the percent in urban areas, right? So, and I was assuming that it was lower in East Africa. I know, like in Uganda, like 90% of the population, I think, is rural. So, okay, good. So that's how you do the C statistic. Logistic regression, tell it to save the predicted probability, then go to the ROC curve, and it will generate the C statistic. If you're running logistic regressions in your capstone, you will indeed need to have the C statistic calculated. Don't think we're done just because you see this slide. You're just getting a little breather and a full sense of security. The really cool Thanksgiving banter is material is coming up. Projects. SPSS outputs for all analyses need to be attached as appendices. Now, these are going to be submitted to Blackboard, but they not only may be attached as a separate file, but maybe it's better that way. But your output should be in one file. So, just make it work. So when you have all your your descriptives, your bivariable analyses, your regressions should really be together in your outputs. Now, if you save those outputs, when you save them in SPSS into different output files, or you saved it, you copy and pasted it into Word, you printed it out as a PDF, whatever you do, there's a way to combine it, okay, to get it together. But please do not include outputs from analyses that don't end up getting used. I don't want to see 6 runs of a regression, only one of which is correct. Okay? Only the ones that ended up counting. That goes into the outputs. Okay. The body of your project is not going to have outputs. You're going to have tables, as I've been showing you what those tables should look like and the structure of them. But there'll be tables. Here I have now 8 to 10 double-spaced pages. That's not including tables. Okay, 8 to 10 double-spaced pages is supposed to mean text. It's okay if it's a little shorter, as long as it's done well and you really cover what you need to. But it is supposed to be a real write-up. It's supposed to have sentences. Sentences correctly formed according to general rules of English grammar and not the general rules of statistical talk. I want it to be able to be read. Okay. So it doesn't mean there may be certain spot or two or something where you have some bulleted points, but basically it is supposed to read like a paper. These dates are wrong. Okay, I did not update this slide to this year's dates. On your syllabus it says. I have to recheck it because the problem I have this year is that we're like the last day of finals or something, and the grades have to be turned in really, really fast. So I have to check. Like, the grades have to be turned in. I'll have to check on it whether it's Wednesday morning at 11 or Tuesday. So I have to check. If I have to get the grades in by Tuesday, I can't have you turning in papers on Tuesday. Right? I won't be able to do it. Now, keep in mind the following. If turning it in, a couple days later is going to mean you write up a better report, then do it. And if you turn it in late, what will happen is you will have an incomplete for a few days to a week or whatever it is you turn it in. I'll have to get a grade in by the deadline, and then when I get it, within a couple days to a week, I will grade it, change the grade online, it gets changed right away. If you're trying to graduate in January, that's not a good option. If you're doing the graduating kind of in January with the waiver of registration, so it's technically a May graduation, but you turn everything in by the second week in January, then having a week later doesn't really matter. Is anybody trying to graduate with January through regular or waiver registration? That's not a common issue since this is usually taken earlier in the sequence. So, okay. Anyway, I'd rather see papers turned in a few days late and be worth waiting for. But that's your call. And keep in mind, once it's late, it's amazing how easy it is. Like, the pressure to get it done, like the urgency, subsides. and the momentum disappears. So if you really keep working on it and you turn in within a couple days, that works. Once it goes beyond that, then a lot of times I find the trade-off isn't worth it because you start losing the feel, and then your devotion to it ends up dissipating. So you'll keep in mind. So all I need to do is, for you, is one, about the article review I mentioned, but also I get to check on the dates for submitting the paper. I had something on the syllabus, and I'm pretty sure at the time I made the syllabus, I did indeed confirm that when the grades were due in. And I had this nagging, terrible, awful feeling that it was due the next morning, which is outrageous, right? Because how can you have a final exam in an afternoon, which could be a large class, and if everything grades turned in the next morning? That doesn't seem reasonable, but I'll check, and I will get back to you. Right, so we've talked about odds ratios. Oh, one more time. There you go. Even when you get the words out correctly to state it, that it's 2 times the odds, the problem is, right, you still want to think of it as it's 2 times the risk. It's 2 times as likely. But it's not, right? So that's a problem, right, with the odds ratios. So it would be nicer to be able to talk in terms of what would you refer to as either a risk ratio or relative risk, where we're actually saying not 2 times the odds, but 2 times the risk, right? And we can't get that from logistic regression, but there is another way. Yeah! All right. Don't we feel great? Relative risk! Yay! Have a hand for relative risk. Yeah! Okay. Or risk ratio, same thing. Okay. So we use statistical alchemy. We take odds ratios and we turn them into gold. So there's a couple ways to do it. Actually, let me check on, am I showing one way or 2 ways? Okay, so this will be one of the 2 ways. One of them is to do what's known as a log binomial regression. It's not nearly as bad as it sounds. Well, okay, maybe it is. But in any case, but when we talk about the, log binomial regression is that we will end up with the coefficients will exponentiate, but instead of getting like the exponent of b to get an odds ratio like in logistic regression, we're going to get the risk ratio or relative risk. So so what I'm going to use is the esophageal cancer data. Do you have that? It's been used before. I don't know if you still have it because I was using homework, right? But maybe we didn't use it in class. It was a homework problem, wasn't there? Was there a homework assignment early? No? I don't think so. So, okay, well then you'll just watch. Esophageal cancer. This is the result of the regular odds ratios from the logistic regression. And we get some odds there. And the outcome was esophageal cancer. Now, if you're going to have a group, if any time the outcome is uncommon, it's a very small percentage, the odds ratios and the relative risk will be very similar. Okay? In which case, the logistic regression works pretty well. The problem is when it's not so small. So yeah, if it's a 2% probability, it's not a big deal. If it's 10%, it starts to be a real difference. If you've got a 20% chance, then it can be quite a large difference. Once you get numbers up there, so like one problem I was looking at, analysis I was doing recently, an odds ratio of 2 corresponded to a relative risk of 1.2. So instead of having twice the odds, but it was 20% additional risk. Right? So there's, you can have a big difference.
So, and this is, right, so there's going to be two ways to, two different methods we can use to really get those relative risks. This is supposed to be the preferred way. I say supposed to be because it often doesn't work. If it works, then it's great. But the model is not very stable, and a lot of times when you try to run it, it may not work. So a lot of times I end up just skipping it and going to the second method. But there are certain properties that make this preferable. So if you go to analyze generalized linear models, then we can select generalized linear models, which is not only the main term, but it's the subterm as well. And you're going to get this screen. We'll just call it a screen. And we'll see it has lots of tabs. Not nearly as friendly looking as the rest of SPSS. And we're going to click on custom. What we're going to tell it is by the distribution, binomial, we have the outcomes are 0, 1 variables, right? It's a dichotomous outcome. But we're going to tell it to do a log transform model. We have to take it tab by tab. So when you try to do this, you're just going to follow along very closely, right, with what I lay out for you here. Your dependent variable here, that's your outcome variable, was esophageal cancer, yes, no, whether they had it or not. Okay, that's good. So far, so good. Okay, and then this is you can binary reference category. You can click and so you can on it and pick the reference category. Go to predictors. Do you remember what the difference is between, when we say something is a factor, what kind of variable is it? It's what? Okay, but what's the nature of the variable? Whether it's independent or not depends on how you use it, but it's what? Yeah, it's a grouping variable, so it's usually going to be categorical, or it could be dichotomous, but one or the other. It's not going to be continuous. Dichotomous or categorical, right? That's all about factors. When we call things factors, it means they're going to be some kind of grouping. As opposed to the generic sense, when people say, here are factors associated with these outcomes. Well, from the social science literature, when you say factors, factors are specifically going to be these categorical variables. So you can list some covariates. Then he goes to the next one, what's the model? And from your pool of factors and covariates, you tell it which ones you're going to use. Exponential parameter estimates. So we're going to check off include exponential parameter estimates we want because we don't want the transform model. We want to get the relative risk, not so we want to do the e raised to the b. Okay, let's just get to, we want to get to these outputs. So when you run it, you'll get regression outputs. And this is for the model we just run. And again, like the others, right, we're basically using those last 4 columns. So just like in the odds ratios, it looks very similar, right? I mean, the structure of the table of the output is very similar. It's the same headings for the right? So here, though, in the log binomial model, this is going to represent relative risks or risk ratios, and the other one is odds ratios. So when you look at the numbers, right, look how they compare for the same variables. For high tobacco consumption, high alcohol consumption, see how the odds ratios compare to the relative risks. Okay. So, Ashley, can you tell me, what do you notice about the difference between the odds ratios and the relative risks? The odds ratios are greater, and in this case, it's just greater, but the real point I want to make, because in these cases, these were both associated with increased risk, the idea is that the odds ratios are going to be more extreme than the risk ratios. Right? The odds ratios are, where's the relative risk? The odds ratios move further from 1 than the risk ratios. It could be on the low side. Right? If the odds ratio was 0.3, the relative risk might have been 0.6. So the odds ratio could be bigger or smaller, but the idea is that it's further from 1. It's exaggeration of the relative risk. Now, this case was not a general population esophageal cancer. There was like a bunch of cases that they had, and they got some controls, whatever. So the percentage of people with esophageal cancer in this group was not really small. That's clear because if it was using just a general population with a very small percentage of people who have had esophageal cancer, then the probability outcome would be small, and those numbers would end up being very similar between the odds ratios and the risk ratios. Here they're not. So the odds ratio was almost like 1.9 for tobacco. The risk ratio was 1.5 about. 5.6 for high alcohol, 3.3. Okay. That's still pretty darn big, right? But now at least you can talk to people and say, you drink a lot of alcohol, you have 3.3 times the risk of esophageal cancer. That's a much nicer way of talking than to say that people who drink a lot of alcohol have 5.6 times the odds. And if you say 5.6 times the odds, you know they're thinking 5.6 times the risk. But it's not true. Now, keep in mind, because this is also important for interpretation, that if you're going to look at both characteristics, you can multiply. So you can multiply the odds ratios or risk ratios. So that if you want to look at, what about people who drink a lot and smoke a lot? What happens to their risk? How are they different than people who do neither? Well, you have about 1.5 times the risk because of your tobacco, another 3.3 times the risk because of the alcohol. And if you have both, then you would multiply and you'd get around 5. Right? So if you have both, you drink a lot and smoke a lot, then you have about 5 times the risk of esophageal cancer. So that's really useful to keep in mind that you can, when you have multiple characteristics, you're multiplying them. In linear regression, right, you were adding the coefficients. Here you're multiplying the ratios, the odds ratios or the risk ratios. But so if you have both, it would be up 5 times. It's much nicer to be able to say it in these terms. Much nicer. I am going to show you, I'll show you this next week, another one, because like I said, that method doesn't always work. Sometimes it crashes. When it crashes, there's another procedure you can use, very similar in the steps, but using a different kind of regression, using a Poisson regression, and we'll talk about that next week. You should be trying for your projects, if you've got a dichotomous outcome, to be able to run these other models and be able to get relative risks. Okay? It's highly preferable to be able to talk in relative risk than it is to talk in terms of odds ratios. One of the problems you have, well, anyway, all right. So let's go over descriptives for your sample. Right, descriptive statistics, right, are supposed to be for the subset that you're using in your analysis. If you're studying adult African Americans, I don't want to see descriptives for the whole NHANES adult sample, just for the groups that you're studying, right? So you're going to have to use a filter to select the subgroup. One of the things you can do, right, is whatever the condition you'd use for the filter, just make a variable. You could make a new variable, transform compute, and set it equal to 1 if you meet the conditions, and 0 if you don't meet the conditions. Now you have it stored as a variable. Now each session, when you go to use the filter, the filter will be if your filter variable equals 1. And that way you don't have to remember or keep retyping things, especially when you have a bunch of conditions. It's convenient. So, yeah. You had a question? Oh, you're looking elsewhere. I thought you had your hand up. So, okay. If you do the filter, the default is selection is that it's not going to delete anything. It's just for the rest of that session or until you turn the filter off, it's only going to include the observations that meet the criteria. Creating an analytic data set. This is when you feel like, okay, you really know you're done with your recodes, and you know you've got the right subgroup. Most important part of that being, you know you got your recodes correct. Because if it's a question of just you use the wrong subgroup, you can just go back to your data, go back to your data set and make another data and redo the process. But when we make an analytic data set, it's going to be a different file. You're going to save it under a different name. You never want to overwrite, things. So that way, when you subset it and you do your analysis, if you need to go back, you still have that point to go back to. Once you know for sure you're done recoding, though, and you know what your criteria are, inclusion, exclusion criteria. You're including people who have these characteristics, and you want to exclude people who have certain other characteristics. So it's like I'm including the adult African Americans, but I'm excluding those with kidney disease. So whatever. So if there's some reason why certain people you want to exclude, you can do that too. What I suggest is, save the data under a different name, because you want to make sure you don't mess up what you had. So if something goes wrong, you have a good place to go back. Data select cases, which we've done before, and set the if condition so it defines the people you want in your analysis. That if condition may have multiple components. It could be if, parentheses, age greater than or equal to 20, because it's adults. And, the word and, another parentheses, race ethnicity equals 1, because you're only looking at Mexican Americans. Right? You can also have ors. So let's, we're doing, okay, so you may have, for your if button, okay, so let's say the age. So the variables RID, AGEYR is the age at screening, maybe adjudicated age, whatever. But let's say age, and let's say you wanted to do was age is from, somebody had like 6 to 19 years. there's two parts to that. It's not just over 20, under 20, no, it's not just under 20, right? There's a lower end as well. So we have to do two things. So age has to be greater than or equal to 6. It has to be high enough to be into the range. And it doesn't have to be capital letters for and. Right? There. And the age is less than or equal to 19. If it meets both those conditions, then I know they're between 6 and 19. And I've captured that. And that's how I captured the age. If I also wanted to run this for only African Americans, let's say age 6 to 19 African Americans, now what I want to do is put another parentheses around that whole thing. So that's the aged part. That's done. And I also want the race to be right. So then, oh, now I'm forgetting what the race variable was. ORID, ETH. I don't know what it is. I'm sorry. So, okay. Don't remember. I forgot. Is that ETHR1? I forgot exactly what it is. But whatever that race ethnicity variable is, all right, let's say that is equal to, I think 4 was African American, if I remember correctly. Could be wrong, but there. So now I have an age component and the race component, the race ethnicity component. If instead of just African Americans, I also wanted Caucasians, so if it was 6 to 19 and African American or Caucasian, okay, then just having it race equal to 4 wouldn't do the job. I have to allow also for the fact that it could be Caucasian. So now I have an OR ID, ETHR1 or whatever it is, equals to 3, which is Caucasian, I believe. But now, again, put a parenthesis on that whole thing. So once I've got another element, race ethnicity, get a parenthesis around that whole batch. Whenever you're going to mix ands and ors, it's going to be really critical that you have those extra sets of parentheses correct. If all you have are ands, it wouldn't matter. So now we've got, right, we've got the, here we go, sorry. So we have an age component, at least 6, not more than 19. We have a race ethnicity component, either African American or Caucasian. And that would be my if condition. If you want to set a variable to capture this so you don't have to keep retyping it, right? So that just means you would be doing is transform compute, and let's have my, say, my population filter equal to 1 if, and the condition above that we have, right? So if it meets that condition above, okay, and then you can do equals 0 if not that condition. But if you can also just do very simply is first do that pop filter variable. First set it to 0 for everybody. Then do the pop filter equals 1. So basically, anybody who meets the criteria will get a 1 for that variable. And everyone else will be 0 because it was already assigned to 0. So it's, you all start off with a 0, and then you only change it to 1 for the people who meet the filter. Then you don't have to deal with a messy if button, if clause, for the case when the filter variable is 0. So it makes it just a little easier. So if you do that, if you use this method, then you can more conveniently turn the filter on and off in your sessions. Okay. So you can use the filter in select cases. Now, what I'm suggesting is in creating a permanent analytic data set to analyze where you're going to actually delete all the cases that you don't want to analyze so you don't have to bother with filters anymore at all. You've just got the data that you really want. I suggest doing 2 steps. The first pass, set the filter, then check your work. Run descriptives on the characteristics defining your subset to make sure you subsetted correctly. If you said it's supposed to be 6 to 19-year-olds who are either Caucasian or African American, then you run descriptive statistics on age and check the minimum and maximum age, and see that it's 6 to 19. And run your race ethnicity variable and make sure you're only getting entries for Caucasian and African American, and everything else has a 0. Make sure that it was done correctly. If it's done correctly, then you can just go back to the filter again. It's going to default to the same condition you had before. But this time, we can pick, there's an option, instead of filtering out, to delete the unselected cases. So if you just if you're looking at SPSS, if you just go to data, select cases, and that window comes up, the dialog for your filter. So data, select cases, you'll see in the lower right, there's options. It defaults to just filtering out the, whatever it says, something to filter out the cases, the observations that don't meet criteria, the filter, right? But one of the options is to delete the cases that don't meet the, right? That don't meet the criteria. Where it says delete, option is can be used, delete unselected cases. So once you've confirmed, you know your recodings are all done, you know you got the right population for your filter, the right population, the filter's done correctly, you've checked to make sure the filter is correct. Now you could do is delete the unselected cases, right? And then save it. And now this new data file you had already created with at the beginning with the original save as. And it may be that when you do that, it may force it into an untitled name so that you don't have that mistake. I don't remember. But then you can save your work, and at that point you have a file that only has the cases you need for your analysis. If you've got 2 aims and they're being done in different subsets of the NHANES data, so then you'll have to do this twice. And you'll make 2 separate analytic data sets, one for each one. So I know there are some people who are doing something where it's like they'll look at one thing in the whole population to see is there more risk in one particular group, and then they do some other analyses in that one risk group. So it's only looking at the subset. So then it just means you may just want to create an additional analytic set. Okay. How are we doing? So, questions about that? How many people have already done that and created a data set that was with the other cases deleted? See, did I see one timid hand there for a moment? What? Filter, we haven't deleted it. Oh, okay, yeah, I just want you to delete it out. Right. So we're getting to that point. I think, when you get your feedback from your next interim report, at that point you should be able to tell whether you're ready or not. If it's good in the interim report and you know that you know your recoding's already finished, right? The idea is supposed to be at the end of interim report 3 that you're ready to run regressions and you're ready for your final analyses. there's always a not inconsequential number that needs some adjustments, still to make that work. But you then have you should be very close because you'll have the feedback you need to make those final adjustments. And then it's easier to work with the subsetted analytic data set. Okay. Yes, we have a hand in the back. Or are you asking for a prize?
A prize.
Okay. Batteries. I got 2 AAA batteries. And it turns out we think they work. Yeah, go ahead.
If you go back to the projector where you're writing on there, the last section where you have pop filter is equal to 0 and then pop filter is equal to 1.
Oh, so when you do transform compute,
Yeah.
right, you can make a new variable,
Yeah.
and I'll say equals 0 for this population filter, and hit OK. And now that new variable is 0 for everybody. Then go back to transform compute, same variable name, equal to 1 this time, and then click on if and put in the condition. Now it's going to be everyone who meets the condition, meets the filter, that's just the filtering condition. It's the same thing you would have put in the select cases, put in the filter there. Everyone who meets that condition will have a 1 for that variable, and everybody else will have a 0. Now, if you want to use the filter, you can just have if population filter equals 1. To only include the people who meet the criteria. Is that okay? Okay. Now, I think, so next week is the last formal class, right? And part of that class, I want people, so as many people as possible, to be creating those final analytic data sets while I'm here. So during, as part of that session. So that means people get feedback and need to make some changes. You'll also have the support here so you can hopefully make those changes and hopefully be ready to create those final analytic data sets. But because putting together those, right, so you want to check, make sure your filters are all correct and so forth. But you'll get some help with that. Okay. Other questions?
We're getting interim report 3 back this week from today.
Yes. Yes. Lenny has pledged not to sleep until the interim reports are taken care of, and we're meeting Wednesday afternoon to go over them. So before she leaves town, these should be done. It also means is I will be here. I mean, this is sad commentary. I will probably be here Thursday and Friday. Well, Friday morning I actually have a meeting off campus, but Thursday I'll be here. But I'll be here still a chunk Friday. So if people are around and want to get the reports earlier, you can come by. If it's a quick question about something on it, I could probably look it up and see what your feedback is. But I don't think I would be able to have the time to go and scan everybody's and get them emailed each one.